Welcome back to our second segment. We're still looking at exploring electrical fields at a point whereby we have got multiple, charges that create the field, and the common point which is in the field of both. But before that, let's look at the mathematical relationship that exists between, varying distance, the charge, and how exactly that affects the magnitude of electric field at a point. Now, question B says, predict the effect of the following changes on the magnitude of electric field at point X. Now, we are trebling the distance, so language is very important. So if we treble something, it means we multiply it by 3, or it becomes 3 times as bigger, all right? So if we go back to our simulation, right, we obviously use the very same. So it means the distance even becomes greater. So instead of that 144, we make the distance 3 times as greater, all right? So if that is the case, you can see already the magnitude of the electric field at that point gets smaller and smaller. So in terms of our, basic question, if we treble the distance, make the distance 3 times as bigger, the original distance, does the magnitude of electric field at a point increase, decrease, or remain the same? So it starts with that multiple choice. Obviously, if we're seeing that, okay, the further away we move from the surface of the charge, the smaller the magnitude of electric field at the point becomes. So that's the important thing that we also want to highlight there, right? So having said that, let's look at the case, because we're told that at point X, if it's R, it's 5 newtons per coulomb. It means if we treble the distance, the magnitude of electric field at point X 3 times the original distance away from the surface of the charge would be even smaller than 5 newtons per coulomb. Okay, what does that mean? It says here, we know that E is equals to KQ over R squared. Okay, now in principle, we know that this, we are told that it's equals to 5 newtons per coulomb in magnitude, right? So what is important for us is to understand that E and the distance are actually inversely proportional to each other, or E is directly proportional to the reciprocal of the square of the distance. So we'll arrive at trying to sketch a graph that represents that particular relationship. So if it's 3 times as big, what do we have in terms of 5 newtons per coulomb? So it should be in multiples, but do we multiply by a factor that's greater than 1 or less than 1? So if it's going to decrease, it means we multiply by a factor that is actually lesser than 1, which is a fraction, okay? So we'll have K, Q, is still the same charge, divided by 3R, but we square 3 times the distance, the original distance. So what do we have here? We have K, Q over 9 R squared, okay? So I think we're onto something here. We already say it's a 1/9 of the original magnitude of electric field at a point, because we know that this is 5 newtons per coulomb. Then this reduces to 1 over 9, which is 5 over 9 newtons per coulomb, okay? So this is the new magnitude of electric field at a point, which is actually lesser than when we double the distance. So if we can go back to that question and actually say, okay, what is the magnitude? It's 5 over 9, right? 5 over 9 Newton per coulomb, that's the magnitude. We didn't say anything with respect to the direction. What about if we make the distance 4 times as big? We need not go back to the simulation now, because we've picked up the pattern. So if it's 4 times as big, what are we saying here? We are simply saying that it's going to be KQ over 4R squared. So we're squaring 4R. So this is like 5 over 16, okay, newtons per coulomb. So it's even smaller and smaller. Now, we can arrive at a point where we say, okay, so if that's the case, so we've used the PhET simulation as we have shown earlier. So we are saying that one of the factors that affect the magnitude is actually the distance. So we've realized that electric field at a point, this is our E, right, is inversely proportional to the square of the distance. Hence, we are saying E is inversely proportional to the square of the distance, right? So this is the mathematical relationship that we were trying to explore, right? So let's understand that. So but this is only true if we keep the magnitude of the charge constant, okay? So this mathematical relationship of if we increase the distance, what happens to E? If we decrease the distance, what happens to E? Can only be true if we only vary the distance and keep the magnitude of the charge that creates the field constant. Now, this takes us to something that is very, very critical in terms of scientific inquiry or, experiments, investigations, where we talk about variables, okay? We've got three types of variables, just as a reminder. We've got the independent, the variable that we were manipulating or changing, right? And then we've got the dependent, which is the response variable. So once again, in this particular exploration, we looked at varying distance or changing the distance from the surface of the charge and seeing how it affects the magnitude of electric field at that point. So wait a minute. So if we change the distance and see how it affects the magnitude of E, we are saying the distance is the independent variable, while electric field at a point is the dependent. What did we keep the same? Okay, we did not change the magnitude of the charge Q. So the magnitude of charge Q was actually our controlled variable in this case. Hopefully it makes a bit of sense, okay? Now, if this is the mathematical relationship, now we want to sketch a graph that shows this relationship. So we've already identified our variables, and we know that for a graph, there are very important components of it. Number one, the title, which is E versus R squared, all right? This is what we are saying. Okay, so on the vertical axis, we've got the dependent variable, which is E. We must also indicate the units of E. The units of E are in Newton per Coulomb, right? And then on the horizontal axis, what do we have? We've got the square of the distance, all right, which is R squared. This is in meters squared, right? Those are the units of our independent variable. So this is the mathematical relationship that we managed to obtain. All right, but then one may say, okay, what if we talk about the relationship that exists between E versus 1 over R squared, okay? So 1 over R squared and E are actually directly proportional. So we'd have something of this sort. So we've got our E, once again, in Newton per Coulomb, okay? And then we've got 1 over R squared, okay? This is per square meter, okay? Those are the units. Take note of that. And then there's a linear relationship between those two. So we need to be very comfortable as far as understanding, because the whole concept is about these relationships. So as long as we are comfortable with that, we are able to make predictions as we demonstrated in the previous question, right? Okay, and then it goes further now. We are onto something a little bit different. Okay, let's try and see what exactly and how unique is this scenario different from the previous one. X is still a point. I'm going to highlight that because there's a major issue regarding, a point and a charge. There's a point charge in space. What exactly do we mean by that? We're saying at a certain point in space, at a certain position, okay, we've got a charge, all right? And then if we place a charge, we call that charge a point charge, okay? And then we can talk of a point in the electric field. It's X. There is no charge there. It's just a position relative to the charge that creates the field. So that needs to be kind of very clear from the onset, right? So X is a point that is still at a distance R, okay? There's charge Q. We assume that charge is going to create a field, right? If the magnitude of electric field X is 5 newtons per coulomb, so we're saying E at point X, or E due to Q at point X, is equals to 5 newtons per coulomb. Once again, that's the magnitude, okay? Whatever the direction is, for now, we're not interested in that, okay? But remember, electric field at a point is essentially a vector quantity, right? So it says here, predict, again, predictions, predictions, and more predictions. And these predictions, as we have grown to understand it, they essentially talk about the relationship that exists between physical quantities. So now we are exploring the effect of changing the magnitude of the charge versus the electric field at a point, okay? Now it says here, predict the effect of the following changes on the magnitude of electric field at point X. Now, we double the magnitude of electric charge, okay, Q. So, if we double the magnitude of Q, so we have E is equals to K, Q over R squared, right? Now, nothing was said of the distance, so we'll keep the distance the same. Okay, so we know that this E is actually equals to 5 Newton per coulomb in terms of magnitude, okay? But now, if we double the charge, the question that remains, basics, does the value of E at that point increase, decrease, or remain the same? That's the line of thinking that we want to assume or want to use. So if we double the charge, does the field become stronger? Definitely does. So at the same point, using a bigger charge, we actually have a case whereby the force that a unit positive charge experiences becoming, correspondingly greater, right? So if we double the charge, what effect do we have there? We then will have K2 Q, that's the doubling part, okay, over R squared, okay? So this is like 2, okay, K Q over R squared. So this is actually double 5 newtons per coulomb, which is equal to 10 Newton per coulomb in terms of the magnitude. So once we double the magnitude of the charge or increase, so doubling is essentially increasing the magnitude of charge, okay? So a bigger magnitude of charge at the same point will have a stronger electric field at the same point, right? So that's exactly what we're talking about. Now, if we have it, it means, again, corresponding, I think we get the trend now or the pattern. So if we have it, what's going to happen? The magnitude of the electric field at a point will also decrease. Having is a decrease. So that's where it all begins. So a decrease in the magnitude of the charge that creates the field correspondingly or consequently would affect the magnitude of E by also decreasing it, okay? Are we onto something here in terms of the pattern? And then C says, making the charge Q 3 times as bigger, okay? Now, if it's 3 times as bigger, it means the also E will be 3 times 5. So here it's gonna be what? Half the original one, which is gonna be 2.5 or 5 over 2 newtons per coulomb, okay? You don't need a calculator for that, okay? And then making it 3 times as bigger is going to be 3 multiplied by 5, okay, newtons per coulomb, right? So if that happens, then we get 15 newtons per coulomb, right? So what are we on about here? We are saying that the mathematical relationship that exists is that once you increase the magnitude of the charge that creates the field, at the same point, the size of electric field at that point will be correspondingly greater, right? Having said that, we'll come back after the short break where we'll look at, the actual concept of E net. Let's take a short breather for now.